Hi everyone, and welcome to this tutorial of large language models. In this tutorial, I want to introduce lm-eval-harness, which is a framework for evaluating large language models. In this framework, I want to show you how to set up lm-eval-harness, and also I want to show you how we can use it for specific tasks such as reverse engineering, which is our favorite task. So first of all, we should know what is lm-eval-harness. lm-eval-harness is an open source framework for evaluating and benchmarking large language models. It lets you evaluate different models through a unified interface. Basically, lm-eval-harness helps you to get rid of writing a separate script for each model. So you can have a unified interface and run any model you want without writing a new code for a specific task. For example, imagine that, as you can see at the right side, imagine that one person wants to use GPT-4 to evaluate a specific task and the other person wants to use llama 3. So we have to write different codes, different prompts, different metrics, and it's kind of messy. So lm-eval-harness helps us to basically make this process pretty easy. But how the lm-eval-harness workflow works? So it's pretty simple. You can simply just install it, and in order to run it, you have to use a prompt, a command. And this command, this is one of the examples of the command that you can use. And as you can see, here we have a parameter called pre-trained. And this pre-trained is the name of the large language model that you want to use. If you want to use llama, here we use llama 3, and the 8 billion parameter model. So all you have to do is install the lm-eval-harness, pick your model, whatever model you want to use, and pick a task. What is a task? I'll tell you later. And then run and save the results of the responses of the LLM. One question that comes to mind is that for running lm-eval-harness, I just read to run a command like this. So where is the data set? Where is my prompt? How I can customize this framework. Before that, I have to explain what is a task. So a task, lm-eval-harness has some defined tasks, which is, for example, for some well-known benchmarks and data sets in the domain of, for example, NLP, the data sets that are widely used by researchers, and the models that are widely used by researchers, they define a specific task for each of them. And we have a big list of tasks in lm-eval-harness. So a task is a benchmark data set, a prompt template, and a scoring metric, and all of them comes to a reusable config. So each task has a config file, and in that config file, you can see how to run that task. You will tell the lm-eval-harness that run this task this way. I'll show you all these examples practically. This is one of the examples of a task in lm-eval-harness. The task name is baby. This is a task for synthetic question answering benchmarks, and this is one of the samples of this task. The input is Mary moved to the bathroom, John went to the hallway, Mary traveled to the kitchen, where is Mary? And the answer that LLM gives us is kitchen. So you can see that it's a question answering data set, and basically it's a text. So you give a short text and a short story and ask a question, and the LLM will tell you the answer. But this is one of the default tasks in lm-eval-harness. Now I want to show you everything practically. So I already have installed lm-eval-harness, but if you want to install it from scratch, that's pretty simple. The first step is to cloning the lm-eval-harness. You have to run this command to clone the repository. I won't do it because I already have it on my server. And then go to the directory of lm-eval-harness, and you can see all the files and directories here. And you have to run this command to install all dependencies, and everything of lm-eval-harness. I won't do it because I already did it. And now once you install it, you will have such a framework. If you go, there is a directory called lm-eval. If you come to this directory, you will see another directory called tasks. And in the tasks directory, you can see all the default tasks in lm-eval-harness. So one of the tasks I told you is baby. If you open this directory, you will see that we have a config file here and a readme file. If you read the readme file, you will better understand what is this task. And if you look at the config file, you will see that this config file actually tells the tells the harness how to run the LLM for this task. So you can see a dataset path, which is the path to the benchmark. This is the benchmark that it will get and download it and run the queries on it. And this is a format of the queries. So basically it's a passage and it's a question and answer. So you saw the format here already. We have a simple story here and the question and then the answer. And we have some metrics. Now I want to run this task using lm-eval command, and I want to give you some information about all these parameters. So we run the lm-eval command. We have the model, which is a Hugging Face model, and the model name is Quen. So here you can change this parameter to any model that you want. And then we define a task. What is the name of this task? And what device are you using? So you can run it on CPU or GPU, but for running large language models, you definitely need GPUs because they are pretty large, and depends on how large your model is. You need a GPU with a bigger RAM. So basically, we know that there are two ways to run the LLMs. One of the ways is by using APIs. And for that API, you need an API key, and commercial LLMs are usually pretty expensive. The other way is that you have the machine with a GPU and download the model locally and run it on your machine. So here I define that I want the device to be a GPU, and the batch size is 4. So batch size is actually the number of samples that we want to process at once. And the limit, because the benchmark might have thousands and thousands of samples. So the limit tells the harness that only run 2 queries. For example, I said like the limit 2, so it will only run 2 samples of that benchmark. And I ask the harness to save the results in this directory. You don't have to create this directory, it will create it by itself. So let me run it. If your model is too large, it takes a lot of time, especially if you want to run it. Especially if it's your first time to run the model and your model is pretty big, it will take a lot of time to download that model because it's usually huge and it can be gigabytes. So don't panic if that happens. And yes, you can see that it could successfully run, and you can see that it only run 2 samples of that data set. And let's look at the result folder, which is here, and it creates baby test result, and we have Quen here. So I previously run this query before. Let me actually remove results and run it again. I want to show you basically that it will create the results baby test as an output directory, and it will save your responses as a JSON file. For this task, because our model is pretty lightweight, it doesn't take that much, but usually it takes a lot of time. And now, if yes, you can see now that the result folder have only baby test, and this is the result of the LLM response. So you have to parse this JSON file. I already wrote a script, Python script, that will print the results into the terminal. So let me run it. I have to give the path to this JSON file, and you can see the results. This is the sentences, these are the sentences, this is a question, and this is the answer, and so on. But this is one of the default tasks in lm-eval-harness that we ran, and I showed you how you can run tasks in lm-eval-harness. Now I want to run our favorite task, which is reverse engineering task. So here I created a data set, a very simple data set of decompiled functions. So I had a binary, I created some decompiled functions from that binary. I get the decompilation using Ghidra. If you don't know what is decompilation and how to get the decompiled functions, please watch my videos. I have a video in my channel about how to use Ghidra for extracting decompiled code. And this is one of the decompiled functions that I have here. And this is the second decompiled function. And I want to use large language models to tell us what this function does and how this function works. Okay, now I want to create a new task in lm-eval-harness, and I want to ask it to run my own benchmark and run my own command. In order to do that, you have to come to this directory, lm-eval and tasks, and you have to create a new folder here. So basically, you have to create a new folder. I already created such folder and I named decompile here. So I created 3 files here. One of them should be definitely the config file. This file tells the harness how to run your benchmark and how to run your command. It's a very important file, so you have to have it. What are the parameters here? So I have a parameter called task, which is the name of a task. This name will be used in the command. I'll show you later. Dataset path. Remember that for baby task, the dataset was mentioned there. The harness will just download that dataset and use that famous dataset. But we want to use our own dataset. So I will tell in the config file, I will tell the harness that instead of downloading the dataset, look at my Python script. And this is the format of the queries, the instruction and the function body, and I have the expected output. And also, so I asked the LLM, I asked the harness to look at this dataset path. And this is the Python script that harness will take a look at it. So here I created a code analysis class, and here I used a library called datasets. Datasets is a well-known library that you can use to load the dataset, to evaluate different datasets. It's a very nice library. So I use such library here to give some dataset information to the harness. And this is I have a description. I tell the harness that this is a set of decompiled functions, and these are the features of my dataset. And these are the parameters of that features of our data set. We have function body, we have instruction, and we have an expected output. And I define a function here which will generate that data set. So basically, split the data set. When you want to use LLMs only for inference, you can just specify that by, test. So this is the path that the harness should take a look at and read all your files from there. So I have decompiled functions folder here, and these are the text files here. So this is where I defined my dataset path, and now I want to generate the examples. So this is my instruction, and the instruction is simply our prompt. I tell it that I want to tell the LLM that you are a reverse engineer analyzing decompiled C code, And please analyze the following decompiled function and describe what it does. This is our prompt, and from that dataset path, I will read these text files and create the features of our dataset, which was function name, function body, and instructions. And I will leave this expected output blank because the LLM is supposed to generate such output. Now I can run the command that will run our defined task. So this task will basically run this instruction on this data set, on these decompiled functions. So here I ask the lm-eval-harness to run one of the Hugging Face models. This is the name of the model. As I said, you can use any other models. This is a task name, which is decompiled functions. I define it in the config file, and I ask it to include the path to our task. And also I mentioned to use the GPU batch size, and also I ask it to save the results in this directory. Let's run it. Because it may take some time, I will pause the video and we'll be back right after I get the answers. All right, I'm back, and you can see that it's done. It takes around like 3 minutes, and I print the results of one of the results of the LLM response, and you can see that it just simply says that it's a and returns a Boolean value. And you can see that it just simply define each task step by step, and basically its definition is pretty meaningless, and the output is frustrating. But I want to show you an output of another LLM, which is Cloud, for this decompiled function. And I want to show you how much the performance of LLMs can be different. Depends on how large the model that you're using, and what model you are using. And you can see that this model, Claude, simply says that this function is a byte-by-byte incremental state machine for parsing a communication frame or packet, similar to a serial link protocol receiver. So it's mentioning that this decompiled function is doing some communication protocol, which is pretty interesting. The second function, I also gave the second decompiled function, and the summary was interesting. This is a physics animation update function, likely from a game engine. It computes a character or object's movement rotation. So you can see that it's mentioning that this function is doing it's calculating something about like movement, rotation, and stuff like that. Now I want to tell you that these two functions come from a robotic firmware. Interesting, right? So from high level, this LLM could understand that this function is a communication function, this function is a navigation function, and the binary that I created, that I used for this video, came from the ArduPilot dataset. It's a pretty well-known dataset for robotics. And you can compile it for different devices and different boards. You can compile their binaries, get the firmware, and analyze it. So these were two decompiled functions from ArduPilot binaries, and one of them was a communication protocol, like sending packets, and the other one was like rotating and navigating the robotics. As you could see, depends on how good your LLM is, the results can be very different. If this video was useful and helpful, please subscribe the channel and support the video. Also, if you want me to create another video about evaluation of different models, such as Quen, Codestral, and use them for reverse engineering, please let me know and comment below this video. And thank you so much for your attention.